Hello, welcome to lesson 4 in this series on particles. We'll talk about ions and charge to mass ratio, which is sometimes called specific charge. So we'll start with what ions are and some terminology and notation that we use. Then we'll briefly cover ionisation and say what ion pairs are. Then we'll talk about charge to mass ratio, or specific charge. As we work through, some questions for you to try, so you'll want a pen, paper, and later on the questions need a calculator. Let's start. So what is an ion? Well, it's simply a charged atom or charged molecule. Now we'll extend that definition a bit later on, but for the moment an ion is a charged atom or charged molecule. Let's take a look at how this happens. Let's start with a neutral helium atom. So it's not an ion, it's got no overall charge, it's neutral. And any neutral uncharged atom contains equal numbers of protons which are positive and electrons which are negative. So if we look at our helium atom, there are 2 protons in the nucleus. In relative charge units, the charge is +2, 1 unit on each proton. The 2 electrons are in the atom. They have a charge of -1 relative unit each. The charge on the 2 electrons is -2, so it's fairly obvious that the total charge is +2 plus -2, which is 0. So it's uncharged because it's got equal amounts of positive and negative charge. Now the thing about an atom is it's relatively easy for atoms or molecules to gain or lose outer electrons. These electrons can get knocked off. It's possible to add an electron to an atom. It's actually very difficult for the atom to gain or lose protons or neutrons. So the thing about an atom is the electrons can relatively easily be knocked off or acquired. So let's take a look at our helium atom, and let's suppose it loses an electron. Let's get rid of an electron, and we're left with this. What have we got? We've got 2 protons, total charge of +2 relative units. We've only got 1 electron, that's got a charge of -1 relative unit. So of course the total charge is +1 plus -1, which is +1. So the thing we have on the left has got an overall charge of +1 relative units. And we call it a singly charged positive helium ion. And we could write the symbol He, and on the top right put a single plus sign. Let's look at the name here, singly charged positive helium ion. It's singly charged because it's got 1 relative unit of charge, positive because that charge is positive, and it's a helium ion. It's a helium atom that's acquired a charge. Singly charged positive helium ion with that symbol. If we wanted to put the mass number in, we could use that symbol, that's fine. If you wanted the full nuclide symbol, you could write it that way, that's fine as well. Now let's move on and suppose the atom loses both electrons. So let's get rid of the other electron. We're left with the bare nucleus. Of course the total charge is now +2 relative units. And we call this a doubly charged positive helium ion. Why doubly charged? Because it's got 2 relative units of charge, which are positive. It's still a helium ion. Symbol, we could write He, and on the top right 2 plus. Some people put a double plus sign like that, but I think it's a bit untidy. 2 plus is good. And this is a basic bare nucleus. If you recognize this as an alpha particle, that's fine as well. In certain circumstances, when this is produced by radioactive decay, you get this structure, it's an alpha particle. But for the moment, we'll call it a doubly charged positive helium ion. Okay, did you get that? Let's try a question. Let me read it through and you can try it for yourself. How many electrons are there in a doubly charged negative oxygen 16 ion? and I'll tell you the atomic number of oxygen is 8. When you've done that, what would be an appropriate symbol for the ion? Have a think about that, pause, and I'll tell you the answer in a moment. Well, I hope you tried it. Let's work through the logic. The atomic number of oxygen is 8, you tell that. So you know the charge on the nucleus is plus 8 relative units. There are 8 protons. That means if you have a neutral atom of oxygen, there'll be 8 electrons. But we've got a doubly charged negative oxygen 16 ion. What's happened to make it doubly charged? Well, someone's added 2 extra electrons. That's the way an atom can become negatively charged, by adding electrons. And if it's doubly charged, there are 2 relative units of charge added, and there must be 2 electrons that have been added. So that means our neutral atom had 8 electrons. Because it's now doubly charged and negative, we must have added 2, so in total there are 10 electrons. That's the answer. And what's the suitable symbol for this? Well, O is oxygen. You could put the full nuclide symbol, atomic number and mass number. On the top right, the important bit is to put 2 minus to show it's doubly negatively charged. You could have written that, that's fine as well. You could have written that where you have 2 minus signs on the top right. I think that's a bit untidy and it could be misread as a single minus sign. So the best notation in my opinion is the notation on the left, one of the first 2. Let's talk about ionisation and what we mean by ion pairs. Ionisation is the process which creates ions, and it normally means the removal or addition of electrons from atoms or molecules, the removal or addition of electrons from atoms or molecules. And in physics we're particularly interested in the removal side of things. That's because we deal with things like collisions between atoms where electrons get knocked out, they get removed. So I'm going to focus on the removal side. So for the present discussion, ionisation we're going to think of as the process which knocks out electrons from atoms or molecules. Now, to knock an electron out requires some energy. If you think about it, the electron is attracted to the nucleus, so there's a force of attraction between the electron and nucleus. We're going to have to supply energy to pull out an electron. Energy is needed to knock out an electron from an atom or molecule. Where does the energy come from? Well, the energy is supplied by, for example, a collision between 2 moving atoms. Bump into one another. If they're going fast enough, an electron, or even more than one electron, can get knocked out from one or other of the atoms, or both of the atoms. It could be a collision between some other particle and an atom. For example, an atom could be hit by a fast-moving electron. It could be a photon that comes along. For example, an ultraviolet photon can be absorbed and its energy used to knock out the electron. And there are other ways. But the important thing is ionisation, knocking out electrons, requires energy to be supplied. Let's look at that pictorially. There's our neutral atom. We supply energy one way or the other, and that energy knocks an electron out. What we're left with is a positive ion and the electron. So on the top is the atom missing an electron, so it's become positive, and there's the electron that's been knocked out. And we call those 2 charges ion pairs. And in this sense, an electron is an ion as well. It's often referred to as an ion, even though it's not a charged atom or molecule. It's a product of ionisation, and therefore we call it an ion. Okay, now we can move on to charge to mass ratio, or specific charge as it's sometimes called. This is a little more interesting in my opinion because we can do calculations. Let me give you a definition. What is charge to mass ratio? Well, it's a value, it's a number, and it's obtained by dividing the charge on a particle by its mass. pretty obvious. Charge to mass ratio. The charge divided by the mass. We often give it the symbol Q over M. Q is our symbol for charge. M is our symbol for mass. Now we usually use SI, System International units. We don't use relative units for charge. We use SI units. What do you think the SI unit of charge to mass ratio will be? Pause and think about it before I tell you. Well, I hope you've paused. The SI units for charge to mass ratio are coulombs per kilogram. Charge in SI units is in coulombs, capital C. Mass in SI units is kilograms, so we're dividing charge in coulombs by mass in kilograms. Coulombs per kilogram, which you could write in that format. Coulombs, kilogram to the minus 1. Now we're going to do some calculations in a minute, so before we start the calculation, let me talk about some key values. First of all, the elementary charge, symbol E, is defined to mean the charge on one proton, and its value in coulombs is 1.60 times 10 to the minus 19, 3 significant figures. It's given the symbol E, which is a bit confusing because it reminds you of an electron. That E does not mean electron, it means the elementary charge, which is the charge on a proton. It's that value. If you have a data sheet or data booklet, it will be on there. You'll tend to use it so many times that you'll remember it. That means the charge on an electron is minus E, minus 1.60, 10 to the minus 19 coulombs. Now a word of warning, or note at least, for neatness, the symbol E without a minus sign is sometimes used for the charge on an electron. Now that's technically wrong. So you might find in some textbook the charge to mass ratio of an electron written as E over M. Technically that's wrong. It should be minus E over M. Nevertheless, people tend to do it. If I need the minus sign, I will be putting it in. But if you see it in a textbook, if you see something like E over M written, it means the charge of an electron divided by its mass, if we're talking about an electron. It's time to do some calculations, so you'll need to do some work here. Give me a chance to shut up. So, question 1, put the elementary charge on the top. The mass of an electron is 9.11 times 10 to the minus 31 kilograms, to 3 significant figures. Can you find the charge to mass ratio of the electron? Pause and try it for yourself. Well, I hope you did it. Q over M, we can write that. It's minus 1.6 10 to the minus 19 divided by 9.11 10 to the minus 31. And if you round the answer to 3 significant figures, you should have got minus 1.76 times 10 to the 11 coulombs per kilogram. Another one. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. What's its specific charge? Pause and have a go for yourself. Well, Q over M is 1.60 10 to the minus 19 divided by 1.67 10 to the minus 27. To 3 significant figures, you should have got 9.58 times 10 to the 7 coulombs per kilogram. And it's worth noting what the number means. Coulombs per kilogram. The clue is in the unit. It means if you had a kilogram's worth of protons, the total charge would be that number of coulombs. In fact, that's why we call it specific charge. In physics, the term specific something often means the amount of something per kilogram. So specific charge means the charge per kilogram. Let's do another question. For this one, I'll give you the elementary charge again. I'll tell you the mass of a proton, it's up there. The mass of a neutron is, to 3 significant figures, the same value. And if you want the mass of a nucleus, you add together the mass of the nucleons. That should be fairly obvious, but it's not true exactly. When you learn some nuclear physics, you'll find the mass of a an alpha particle, for example, 2 protons and 2 neutrons, is slightly less than 2 of those plus 2 of those. But for our purposes, it's accurate enough to say if we want the mass of a nucleus, it's the sum of the masses of the nucleons. So let's do a calculation. Find the charge to mass ratios of the following: a helium-4 nucleus and a singly charged negative helium-4 ion. Pause and try both of those for yourself. Let's do the helium-4 nucleus. If it's a Bohr nucleus, the charge is due to the 2 protons, 2 of them. 2 times 1.6 10 to the minus 19 is the charge. The mass, well, I just add together the mass of the nucleons. It's helium-4, 2 protons, 2 neutrons, 4 nucleons. So it's 4 lots of this number. 4 times 1.67 10 to the minus 27 kilograms. As I mentioned before, the true value is slightly less than that for reasons I won't go into here. And Q over M, we just plug the numbers in. If you're doing this on a calculator, put some brackets around, especially the bottom term, or it will go wrong. So put 4 times 1.67 10 to the minus 27 in brackets. If you don't, you will get the wrong answer on your calculator. That should give you a final answer of 4.79 times 10 to the 7 coulombs per kilogram, to 3 significant figures. How about the other one? A singly charged negative helium-4 ion. Well, I hope you can see that it's become singly charged by having an electron added to a neutral helium atom. The charge is simply the charge on one electron, singly charged negative. So the charge on the ion is minus 1.6 times 10 to the minus 19 coulombs. The mass is the same as the previous one, same as the nucleus. Why have I done that? What about the electrons? Well, the electrons are so light compared to the mass of the nucleus that we can ignore them. We're only working to 3 significant figures, and it's perfectly valid to ignore the mass of the electron and say that the overall mass of this ion is simply the same as the mass of the nucleus. It doesn't make any difference to our calculation here if we ignore the mass of the electron. So I'll use 4 times 1.67 times 10 to the minus 27 again. Do the sums, and you should get minus 2.40 times 10 to the 7 coulombs per kilogram. Okay, let's do the final question, then we are finished. I've put the same data up as we had previously, but I'm going to give you a slightly harder question, number 4. Measurements on an unknown nucleus give its specific charge as 4.11 times 10 to the 7 coulombs per kilogram, and its mass 1.17 10 to the minus 26 kilograms. What you've got to do is find the nucleus's proton number, Z, and neutron number, N. So, I'm going to give you a hint in a minute. If you don't know how to do that, you may want to wait for the hint. If you want to go ahead and try it for yourself, you can pause now. Here's the hint. First of all, the charge Q on a nucleus is given by this. The charge is the number of protons, Z, times the elementary charge, the charge on one proton. So if we want the atomic number Z, we can take the charge on the nucleus and divide it by the elementary charge. Now if you want to pause here and do it, if you needed the hint, you can. Let's go through the solution. We're told that the charge to mass ratio, the specific charge, 4.11 10 to the 7 coulombs per kilogram. Let's rearrange that to get an expression for the charge. Q is going to be the mass times the specific charge. Well, I know both of those values. I'll multiply the mass, 1.17 10 to the minus 26, by the specific charge, 4.11 10 to the 7, and that gives me the charge on the nucleus, 4.81 times 10 to the minus 19 coulombs. Now refer to this hint here. Easy to show that the number of protons, the atomic number Z, is the charge on the nucleus divided by the elementary charge. So if I divide this by the elementary charge, I'm going to know the number of protons. Z is that number over the elementary charge. Ignoring minor rounding errors, it's 3. So I know there are 3 protons in the nucleus. That's the first part of the question answered. Find the proton number. We also were asked for the neutron number. Let's just work that out. We know the mass number is A, and to work out the mass number, which is the number of nucleons, all I have to do is take the mass of the nucleus and divide by the mass of one nucleon. Say that again. To find the number of nucleons, the mass number A, we take the mass of the nucleus and we divide it by the mass of one nucleon. And that gives us 7. So the number of neutrons is simply the mass number, which is the total number of nucleons, minus the atomic number. It's 7 minus 3, which is 4. I hope you got that. Okay, we are done. Thank you for watching. I hope that was helpful.